So in this lecture, we're going to talk about kind of how computers store numbers and different types of errors that can occur in finite precision computing. This is in preparation for discussion of several different numerical methods for solving mathematical equations, essentially. As you probably know, computers can't store or don't typically do calculations in infinite precision. They have a finite precision. And therefore, it's important to understand the different types of errors that we might encounter. The two most important being round-off error and truncation error. So let's look at an example of both of those, each of those. So the way a computer stores numbers is in this type of format. So the S stands for sign. That's just positive or negative, right? The M is the mantissa. That is the floating point representation of a number that will then be multiplied by the base. This is usually 2, but sometimes it might be 10 or 16, depending on the computer architecture. And then again, we have a sign and an integer exponent. And so the smallest number that most computers can store is usually somewhere, at least with respect to the base, is usually somewhere on the order of 2 to the minus 53. Just depends on the architecture and other things. The smallest number that a computer can store that when added to the number 1 produces a new number that is different from 1 is called the machine precision or machine epsilon of the computer. And so in NumPy, we actually have a function that will give us what the machine epsilon of our computer is. So here I've defined it as a Python variable epsilon and printed it to the screen. So the number is, in this case, 2.22 e to the minus 16. So this is the smallest number that when I add it to 1 will produce a number different than 1. Turns out that this is 2 to the minus 52 for my computer here. We can verify that that is true by just setting up some simple Python conditional statements. So if I add 1 plus epsilon and compare it to 1, we can see that if I say 1 plus machine epsilon is not equal to 1, we get true, so that our statement is true. Epsilon plus 1 gives us a number that is different from 1. Okay. However, if I divide epsilon by 10 and add it to 1, then you see it's identically equal to 1. So the machine epsilon divided by anything, in this case I chose 10, but divided by anything is going to just return 1 when added to 1. So we're just verifying that that is, in fact, the smallest number at which a computer can store. And because the computer can only store a finite precision, numbers down to a finite precision, or have addition to numbers differ by a finite precision, that is machine epsilon, then there'll always be some round-off error, right? So in this case, if we needed to compute numbers that were smaller than machine epsilon, then we would have trouble doing that with the finite precision that I have on my computer here. And this is true, of course, of all computers doing floating point arithmetic. So that is where round-off error comes from. The other type of error is truncation error. And truncation error is the error we often fight as a numerical analyst, because with respect to truncation error, it's often us that are making decisions about where to cut off or where to terminate algorithms given some finite finite precision, right? So let's look at an example where we are evaluating the Taylor series of sine of x. So in this case, I'm only printing out the first 7 terms of the polynomial, and we know that a Taylor series only approximates only when it is extended to infinity does it approximate the function that it's designed or set to approximate exactly, right? So in this case, if we have our Taylor series, which I've printed out here, and I've created a function in Python that will allow me to generate it, again, in this case, only up to the first 9 terms. If we evaluate that function, then at 0, if we evaluate that function at pi over 2, we know that the sine of pi over 2 is identically equal to 1, right? So if I take no terms in the Taylor series expansion, then my leading term, what I'm showing here is 1 minus the Taylor series expansion of sine. And so 1 minus 0 is, of course, 1, and I have an error completely of 1. Although as I increase the number of terms, so here I have the Taylor series representation. Again, this is 1 minus the sine of x. And so you have this, and in this number, in this case, the error is small when I take 4 terms. And as I go on and take more and more terms, the number approaches eventually, if I took enough terms, it would approach machine epsilon. And I don't think I take enough terms for that to happen here. But as you can see now, with 19 terms in the Taylor series, I have a very, very small error when evaluated at pi over 2, which we know, again, is identically 1. So this is a representation of truncation error. In this case, we are truncating the Taylor series at some finite level, and the error that's left over is something that we have to live with. And it's something that we want, we choose to minimize, always in contrast with the speed of our algorithms or the stability of our algorithms. The speed should be apparent, of course. If I have to evaluate 100 terms of a Taylor series to get the accuracy I need, that's going to be much slower than if I only have to evaluate 2 or 3 terms to have an acceptable accuracy. We will discuss stability in one moment. The next slide is just another example of that. So if I only have 3 terms of the term sine, in this case I'm not evaluating it at pi over 2, but rather just showing the full curve for a full periodic cycle of the sine wave between 0 and 2 pi. And now if I take more terms, you see I begin to approximate the function better and better, such that by the time I get out to, say, 19, 20 terms, that it does a really good job approximating sine for the entire period there. So this is just a graphical representation of what I was discussing before with respect to truncation error. So usually truncation error and round-off error don't interact with one another. However, sometimes round-off error can cause numerical instabilities to occur in algorithms. And so let's look at an algorithm that we would use we could use to compute powers of the so-called golden mean. So it turns out that this function right here, this number right here, is called the golden mean. And we could verify that if we wanted to compute the power of this, so in other words, phi to the 0 power, phi to the 1 power, phi to the 2 power, phi to the 3 power. If we wanted to compute those, we can actually verify that this recursion relationship will work in the sense that if I evaluate phi 0, of course that's 1, and then phi at 1, this evaluates to 0.6 something. Then if we were to take those two, plug them into this formula, I would get the value of phi at, so phi at 0 here, phi at 0 here, phi at 1 here, I could evaluate or get an approximation of phi of 2 here. And so let's look at this in terms of numerics. So the first thing we'll do is actually compute all of the powers individually. So we're not going to use that formula or that what we'll call recursion relationship right now. We'll actually compute the powers. And the way we'll do that, right, of course, we'll use NumPy and do some broadcasting. So we have the square root of 5 over 2 minus a half, all to the power of a NumPy array that goes from 0 to 79 in this case. And so if you wanted to see that, what that is exactly, you could look at it like this. So there is our number again, so phi to the 0 power would be 1, phi to the 1 power would be 0.618, and again, just continuing on. So here we're not using the recursion relationship, but rather explicitly computing the powers using NumPy broadcasting. Next, we'll calculate the first two powers in closed form. So the first thing I'm going to do is store an array of zeros that will store the recursion relationship. We'll call phi recursion here. And of course, as we know, phi at 0 is 1, and phi at 1 is just the evaluation of this function, the square root of 5 over 2 minus 1/2. So those are our first two values, and we'll use those first two values to compute the second, third, fourth, fifth, sixth, all the way up to the 79th value, right? And so this is our recursion relationship. And in this case, we won't look at the output except to look at it graphically on the next slide. And here's what we have. So there you have the two lines, a blue line, which represents the exact powers, right? And a orange line that represents the recursion relationship. And you see that for small numbers, for a small n, this works really well. The recursion relationship gives the exact value. But somewhere along the 55th to 60th power out here, we begin to get these spurious oscillations in our recursion relationship results. Again, you can see the exact result behind it, the blue line there. And this is due to the sort of buildup of round-off error in our computation. And eventually it becomes unstable. And so in numerical methods, we always are fighting a battle of stability versus accuracy versus speed. You can, in very select circumstances, maybe improve two of those at once. But it's virtually unheard of that you could ever improve them all simultaneously, meaning design an algorithm that is as fast as possible, as accurate as possible, and as stable as possible. There are always trade-offs among those. And it's those things that is really the reason why we want to study numerical methods, because you have to have some, if you're going to use these type of computer solutions to problems, it's important to understand the trade-offs between accuracy, stability, and speed so that you can get solutions that are of acceptable accuracy in an acceptable amount of time. And of course, be wary of any kind of instabilities that will occur. And so with that in mind, as we move forward through the rest of the course and we discuss the exact algorithms, we'll always return to these ideas of accuracy, stability, and of course, speed.